Hi, my name is Lily Alterman, and today I'll be presenting to you Lab 1 Constant Velocity from Physics 2211. Now, the purpose of this lab is to observe the motion of an object moving at a constant speed without changing any directions. And the other goal was to use the data we gained from this to create an analytical model and basically create a representation of this motion. This lab uses two fundamental physics principles, Newton's first and second laws. Newton's first law states that objects in motion or at rest stay in motion or at rest unless acted on by an outside force. Newton's second law, also known as the momentum principle, relates the total interactions to the changes of the motion in the system. So basically, how these added forces in the system affect our momentum and how the object travels and moves. This is related to the formula F net equals the derivative of momentum over the derivative of time. Newton's second law also gives us the velocity and position update formulas, which basically allow us to predict the final velocity in the system and also the final position in the system. Also, additionally, if the net force is a constant velocity, then it can be found the following way by using the velocity average formula by taking the initial velocity plus the final velocity and dividing by 2. Net force, if it is equal to 0, always results in a constant velocity. Now for this lab, we'll be using the following programs, Tracker and WebPython. Tracker is able to analyze videos of motion and then give out the position and relative velocity and timestamps. WebPython allows me to use Python to basically code a simulation representing the motion. And these programs will provide a slightly different result in the motion of the object, and we'll get into why those differences happen in the later slides. And also, the object's motion that will be studied is this little peanut car pigeon. The initial conditions of this experiment is that the system has the object in motion, the peanut car, and around the system was also a tape measure. Now, the assumptions I've drawn is that there was no air resistance, friction, or any additional forces in the system. That means also all the forces, the net forces equaled 0 for there to be a constant velocity. I also assumed that the floor was flat, at least that is what Georgia Tech dorms tell me. And then I assumed that the object traveled in a straight line with a constant velocity. Now this is the tracker simulation. Before I play this video real quick, there's two important things to note. Right on this left side over here, this is the actual video of the car moving. In this video, I have used the axis to determine our first main axis will be right here, starting that as the origin point right around here. And over here, this is the list of the times and our x positions right here, and also the related graphs of those. So now if we play this video, you can see the little car going by, running through and getting all this data for us. Now using the previous data gained in Tracker, we can make our WebPython code. So first of all, I took the change in position at the first two coordinates and the change in time to get our starting velocity. That was inserted right in this area of our code, and the initial position was put at 0, 0, 0 or our origin. For the time, I started time at t equals 0, 0, and delta t was equal to basically the frames per second that my video was filmed at, which ended up being 0.033. Now the whole video and part of the video where my object was in frame and was moving was a zero point 0.8 seconds, so that's why I set my while statement to. And then also I updated the ball velocity with Newton's second law formula to put the ball velocity equals the ball velocity plus F net times delta t. And to advance the clock, we are doing a similar thing. It's t plus delta t, which basically is an incremental, ever so slightly increasing the time variable till it gets to this zero point 0.8 seconds. And then the ball's position equals the ball's position plus the ball's velocity times delta t, which was also derived from Newton's second law formulas. Now, this is the WebPython simulation. So as you can see, this is all my code, and scrolling through, and this will then run and show the object moving and get my two charts, and at the very bottom get a whole bunch of data that will be used in the next slide. Now for the comparison of my models, as you can see, this is the computational data. So I got that from our WebPython, and the physical data, which I got from the tracker system. Graph, they both have a similar rate of change, an almost identical rate of change. The only difference right here you can see is the starting values. The tracker data was able to get a more accurate starting value since it was derived exactly from the video. Meanwhile, I did have to use the first 2 points of this physical data to eventually make my starting velocity for the computational model. So because of that, my starting point is slightly off, which does result in the next slide's comparison. Because of that starting value being slightly off, as you can see, the physical model is slightly above the computational model in its linear chart, but otherwise the rate of change is almost identical, and the two lines themselves are very close to each other, making both methods a very valid way of representing the data and making the physical method ever so slightly more accurate. Now to wrap up the lab, we have our what if and what does questions. For the what if question, I answered that the graph of the position would be going in the negative direction. Since when it was going from negative x to positive x, it was in the positive. By reversing that order, it would essentially reverse the graph. And the only thing that would not change is the magnitude of the values here. For the what does it mean question, I said it's not possible to know how many forces are acting on the object because there are many forces that are still unknown, like friction. The only thing we could say for sure though is that those forces are all equal and all cancel out to make the net force 0, so our velocity can be constant. Here is my citation for the image on slide 2 and the web Python link. Thank you so much for listening and have a lovely day.